London. July 7, 2005. A coordinated act of terror changed the city forever. Four suicide bombers detonated homemade devices on public transport, killing 52 and injuring over 700. But what puzzled investigators wasn't just the scale. It was what they didn't find. No traces of TNT. No RDX. No military-grade residues. What remained was almost nothing. A chemical ghost. At the center of this forensic mystery were two deadly, volatile compounds. TATP and HMTD. Their existence exposed a new, challenging frontier in both chemistry and forensic science. Mother of Satan. The chemistry and forensics of TATP and HMTD. Introduction to peroxide explosives. TATP, triacetone triperoxide, and HMTD, hexamethylene triperoxide diamine, are highly sensitive organic peroxide-based explosives. Unlike military-grade explosives produced in specialized facilities, these compounds are often termed homemade due to their synthesis from readily available chemical precursors. Despite their improvised origin, both TATP and HMTD are classified as primary high explosives, meaning they are capable of initiating a detonation, a supersonic shockwave, rather than merely burning rapidly. TATP, in particular, has earned the moniker Mother of Satan due to its extreme volatility and unpredictable nature, making it notoriously dangerous even during its illicit synthesis. Both TATP and HMTD have been implicated in numerous significant terrorist attacks globally, including the July 7 London bombings, the Bojinka plot, and various attacks in Paris and Brussels. Their accessibility from common household or industrial chemicals has made them a preferred choice for individuals seeking to construct improvised explosive devices, IEDs. Historically, the synthesis of TATP dates back to 1895 by German chemist Richard Wolfenstein, and HMTD to 1885 by Ludwig Legler, both discovered during academic research into organic peroxides, not for their explosive potential. Their emergence as compounds of concern in illicit activities only became prominent in the late 20th and early 21st centuries. 1.1. TATP. Properties at a glance. TATP, triacetone triperoxide, is classified as a high explosive and a primary explosive, inherently undergoing detonation. It appears as a white crystalline solid with a faint fruity acetone odor, and is generally unstable and highly sensitive. Its explosive properties are notable. Detonation temperatures range from approximately 2000 to 2800 Kelvin, with a detonation velocity between 2500 and 5300 meters per second, dependent on density. It generates a detonation pressure of 5 to 8 gigapascals and produces a high shattering effect, brisance. TATP's relative effectiveness, compared to TNT, is around 0.8 to 0.9, with a relative energy output of approximately 2,800 kilojoules per kilogram. TATP exhibits very high sensitivity to shock, and high sensitivity to friction, heat, and static electricity, making it exceptionally dangerous. Post-explosion, it leaves very low visible residue as it primarily decomposes into gaseous products, with detectable products including acetone, transient ozone, and trace amounts of TATP itself. 1.2. HMTD. Properties at a glance. HMTD, hexamethylene triperoxide diamine, is classified as a high explosive and a primary explosive, inherently undergoing detonation. It presents as a white crystalline solid with a faint, fishy, amine odor when decomposing, and is notably unstable and very sensitive. Its explosive properties are significant. Detonation temperatures range from approximately 3100 to 3500 Kelvin, with a detonation velocity of 3000 to 5100 meters per second, density dependent. It generates a detonation pressure of 1.5 to 2.5 gigapascals at lower densities, potentially higher at increased densities, and exhibits very high brisance, often surpassing that of TATP. HMTD's relative effectiveness is around 0.9 compared to TNT, and its relative energy output is approximately 3400 to 5600 kilojoules per kilogram. HMTD is characterized by its extremely high sensitivity to shock, very high sensitivity to friction, and high sensitivity to both heat and static electricity, making it exceptionally dangerous. Post-explosion, it leaves low visible residue, primarily gaseous products with some trace particulates. Detectable products include formaldehyde, various amines, and trace amounts of HMTD itself. Chemical structure, properties, and inherent dangers. The defining characteristic of both TATP and HMTD is the presence of inherently weak peroxide bonds. Compared to typical carbon-hydrogen bonds, these bonds are considerably less stable and require significantly less energy to break. This fundamental bond weakness, coupled with the significant internal strain within their cyclic, cage-like structures, makes both TATP and HMTD profoundly unstable and highly sensitive. These molecules are not merely unstable, they're eager to decompose. Internal tension pre-stresses the already weak peroxide bonds, dramatically reducing the activation energy required for their rupture. Consequently, only a small external stimulus, such as heat, shock, friction, or even a static electric spark as low as 1 millijoule, is sufficient to initiate their rapid decomposition. Upon initiation, the stored strain energy is released quickly, contributing significantly to the overall exothermic nature and destructive power of the explosion. A crucial characteristic is that these molecules contain all the oxygen necessary for their rapid, energetic decomposition built directly into their chemical structure. This means no external atmospheric oxygen is required for their explosive reaction. This property allows them to detonate even in confined spaces or under conditions where external oxygen is limited, making them incredibly dangerous in enclosed environments. Explosion mechanics. The chemistry of detonation. TATP's detonation. An entropic explosion. TATP's detonation is predominantly driven by entropy, which manifests as a sudden and massive increase in gas volume. When TATP is triggered, its weak peroxide bonds, requiring approximately 150 kilojoules per mole to cleave, break almost simultaneously, initiating a radical cascade involving carbon-oxygen and carbon-carbon bond rupture. Solid TATP rapidly decomposes into 3 molecules of gaseous acetone and 1 molecule of gaseous ozone. This initial volumetric expansion, which can be 800 to 1000 times from solid to gas, generates a powerful pressure wave before significant combustion or heat release occurs. Microseconds later, the gaseous acetone and ozone react exothermically through secondary combustion, producing carbon dioxide and water. This subsequent heat release further amplifies the destructive force. The immediate gas expansion, followed by rapid heat generation, forms a self-propagating supersonic detonation front. The temperature in the detonation zone typically ranges from 2300 to 2800 Kelvin. HMTD. A more enthalpic detonation. HMTD's detonation mechanism is chemically more complex and is characterized as an exothermic chain reaction, making it more prominently enthalpy-driven than TATP. Its initiation involves the simultaneous rupture of both oxygen-oxygen bonds, also requiring around 150 kilojoules per mole, and carbon-nitrogen bonds, followed by carbon-oxygen bond cleavage. This process decomposes HMTD into a diverse mixture of gaseous products, including formaldehyde, ammonia, methylamine, carbon dioxide, water, and nitrogen gas, with rare traces of nitric oxide and other amine fragments. These molecular fragments undergo rapid oxidation, releasing substantial heat, resulting in a higher detonation temperature, often exceeding 3200 to 3500 Kelvin. This significant heat release contributes to HMTD's superior brisance shattering capability, compared to TATP, with a powerful pressure wave generated by the rapid exothermic burn and abundant gas release. Forensic science challenges. The forensic analysis of TATP and HMTD presents exceptional challenges due to their inherent properties and the minimal, often elusive, evidence left after detonation. Pre-blast difficulties. Precursor availability. The chemical ingredients required for TATP, acetone, hydrogen peroxide, and HMTD, hexamine, hydrogen peroxide, are legal, widely available household or industrial chemicals. This ubiquitous availability makes it extremely difficult for authorities to flag suspicious purchases of these individual components, as they have legitimate everyday uses. Volatility. TATP exhibits significant vapor pressure and can sublimate at room temperature. This volatility complicates vapor detection efforts and makes long-term storage of unexploded TATP challenging, as the material can dissipate over time. While this property aids some pre-blast vapor detection systems, it also means that residues can vanish quickly from a scene. HMTD also degrades, impacting the effectiveness of vapor detection over time. Unreacted TATP crystals, if not properly sealed, cooled, and analyzed promptly, can simply vanish. Post-blast challenges. Minimal residue. Upon detonation, both TATP and HMTD decompose predominantly into gaseous products. This results in minimal to virtually no solid residue remaining at the blast site. This characteristic stands in stark contrast to conventional nitro-based explosives like TNT, which leave behind noticeable soot, unburnt fragments, and distinct chemical residues. The scarcity of solid residue makes definitive identification of the explosive incredibly challenging. Furthermore, scenes involving TATP or HMTD explosions typically lack the widespread soot or charring often associated with other explosive incidents. Risk to handlers. Any unexploded materials or unreacted precursor chemicals found at a scene pose significant detonation hazards due to their extreme sensitivity. This makes handling and evidence collection incredibly dangerous for bomb disposal experts and forensic personnel. Interference. Post-blast samples are frequently contaminated with various types of debris and chemicals from the surrounding environment. These contaminants can interfere with sensitive analytical techniques, complicating the identification and quantification of explosive residues. Analytical chemistry. Tools of the trade. The primary objective of forensic analysis in cases involving peroxide explosives is the accurate detection, identification, and, if possible, quantification of explosive residues or their precursors, both before and after an explosive event. Forensic laboratories employ a multi-layered approach, utilizing a combination of screening and confirmatory techniques. Sample collection and preservation. Proper sample preservation for TATP and HMTD is critical due to their inherent instability and volatility, which can lead to degradation, sublimation, and cross-contamination. Samples must be collected in airtight, inert containers like glass vials with Teflon-lined caps or specialized nylon bags. For storage and transport, samples should be kept cool, ideally below 4 degrees Celsius, refrigerated or frozen, and shielded from light to slow degradation and sublimation, with minimal time lapsing between scene collection and laboratory analysis to maintain evidence integrity. Sample preparation. Sample preparation methods for TATP and HMTD vary based on the evidence matrix. Key techniques include solvent extraction for solid materials, using organic solvents like acetonitrile or diethyl ether to dissolve residues. Headspace analysis, critical for volatile compounds like TATP, where heating volatilizes components for direct analysis or trapping. Solid phase microextraction, SPME, for pre-concentrating volatile and semi-volatile compounds. Solid phase extraction, SPE, for trace detection and cleanup in complex samples. And filtration to remove particulates that could interfere with instrumentation. Analytical techniques. A combination of techniques is typically employed to provide robust and confirmatory results for the presence of peroxide explosives. Screening techniques. On-site or rapid laboratory analysis. Screening techniques are employed for rapid, preliminary detection of peroxide explosives, often on-site or in the early stages of laboratory analysis. Color tests offer quick chemical indications, but their high potential for false positives limits their use for definitive identification. Ion mobility spectrometry, IMS, commonly found in handheld airport detectors, separates ions based on their mobility. However, it often lacks the specificity needed for peroxide explosives, potentially leading to false alarms. Raman spectroscopy and Fourier transform infrared, FTIR, are non-destructive methods that identify compounds by their unique vibrational fingerprints, suitable for bulk material but less effective for trace residues. Lastly, direct analysis in real-time, mass spectrometry, DARTMS, and desorption electrospray ionization, mass spectrometry, DESIMS, are ambient ionization techniques that enable rapid, direct analysis of surface swabs or samples, providing immediate mass spectral data for quick laboratory screening. Confirmatory techniques. Laboratory-based. Confirmatory techniques, typically performed in a laboratory, provide definitive identification of TATP and HMTD. Liquid chromatography mass spectrometry, LCMS/MS, is highly reliable for thermally labeled compounds like TATP and HMTD, as LC's lower operating temperatures preserve molecular integrity, and tandem MS offers high sensitivity and selectivity for trace-level identification. Gas chromatography, GC, though a standard for volatile compounds, can degrade TATP and HMTD in its hot inlet, requiring specialized techniques. However, Headspace GCMS is particularly effective for volatile TATP by analyzing its intact vapor phase. Nuclear magnetic resonance provides detailed structural information, excellent for confirming synthesized materials, but requires significant sample purity and quantity, limiting its use for trace forensic evidence. Finally, X-ray diffraction, XRD, identifies crystalline compounds by their unique diffraction patterns, proving valuable for analyzing solid residues or unexploded crystalline material at a scene. Reporting and interpretation. Forensic reports typically include a clear statement of detection and positive identification, supported by data from multiple analytical techniques and comparison to known standards. If possible, the quantification of the explosive present is also provided. Reports always contextualize the findings and acknowledge any limitations inherent to the analysis, such as the low residue nature or volatility of peroxide explosives. Historical impact. The 7/7 London bombings and forensic evolution. The 7/7 London bombings in 2005 marked a pivotal moment for peroxide explosive forensics. For suicide bombers used TATP-based improvised explosive devices, IEDs, on London's public transport, exposing critical gaps in existing forensic capabilities for these unique compounds. Investigators faced immense difficulties at blast sites due to the near absence of typical residues like soot, nitrates, or identifiable explosive fragments, unlike conventional military-grade explosives. This puzzling lack of evidence initially caused confusion and speculation about military plastic explosives, given the blast intensity. Despite these challenges, meticulous scene work, advanced laboratory analysis, and specialized techniques, including Headspace GCMS, precursor chemical analysis, and sophisticated vapor detection, definitively confirmed TATP as the primary explosive. Traces of HMTD precursors were also recovered, suggesting the perpetrators may have experimented with or prepared alternative peroxide explosives. This pivotal event directly accelerated the evolution of forensic analytics for TATP and HMTD. marking a significant leap in capabilities from 2005 to 2025. The evolution of forensic analytics for TATP and HMTD. 2005 versus 2025. Forensic analysis of TATP and HMTD has undergone a dramatic transformation driven by the unique challenges presented in 2005. In 2005, the primary focus was on bulk materials, vapors, and precursors, utilizing techniques like GCMS, often with derivatization, headspace GCMS, basic color tests, and FTIR, for bulk analysis. Thermal instability frequently caused TATP and HMTD degradation in GC injectors, and detection limits were poor, typically in the nanogram-microgram range. Sample preparation was largely manual, precursor confirmation relied on general chemical class tests, and IMS offered poor sensitivity. Ambient ionization tools were nascent, standardization was lacking, data interpretation was manual, and field kits were basic. Consequently, forensic reporting confidence for peroxides was lower due to volatility and high false negative rates. By 2025, a significant shift has occurred towards highly sensitive trace detection of intact residues, vapors, and surface contaminants. LCMS, MS, is now the preferred lab technique due to its non-thermal operation, eliminating degradation issues common with GCMS, though improved GC inlets are still used. Automated microextraction, SPME, micro-SPE, and direct ionization techniques, DART, MS, DESIMS, QTOFMS, have streamlined sample preparation. Detection limits have improved by 2 to 3 orders of magnitude, now reaching sub-nanogram, picogram, levels with high-resolution mass spectrometry, HRMS, and advanced IMS. Color tests are supplemented by more specific electrochemical and fluorescence-based sensors, and ambient ionization tools are commonplace, allowing direct surface analysis. Critically, ASTM standard E2677, E3245, are globally adopted. Data interpretation is enhanced by chemometrics, automated libraries, and machine learning. Digital sample tracking improves chain of custody, and miniaturized portable MS and advanced sensors enable effective early scene screening. This comprehensive progress has significantly increased confidence and reliability in forensic reporting for peroxide explosives. TATP and HMTD are more than just molecules. They are potent symbols. They represent a dangerous combination of accessible chemistry and destructive intent, highlighting how easily common materials can be weaponized. Yet, they also serve as a profound reminder that while knowledge, when misused, becomes a weapon, science, when applied with purpose and rigor, becomes a shield. As we continue to study their intricate chemistry and relentlessly improve our detection capabilities, we honor those affected by their destructive power. We strive to make tomorrow safer, not through fear, but through the unwavering pursuit of scientific and forensic truth. If you found this analysis insightful, please follow for more in-depth explorations, subscribe to our updates, and share this information with others. I always welcome your comments, questions, and opinions below. Let's continue the conversation on the critical role of science in global security. Thank you for watching.